Well, well, well. Who would have thought, right? Like all those years ago when I was taking Andrew's machine learning course, I never thought I'd be here doing this talk. So just super stoked to be here today. Woo! Thank you, thank you. So hi, everyone. I'm Apoorva, and today I'm going to be talking to you about how to achieve artificial general intelligence. I'm joking. That's too much for a 30-minute talk, and I definitely don't have all the answers, but I'm going to be discussing something that's equally fundamental, which is how to build memory management systems for AI agents so they can truly learn from experience and collaborate with us intelligently in the future. Here's a bit about me. Last year, I moved into my first ever developer advocacy role here at MongoDB. And as a dev advocate, I create technical content, hands-on workshops, and talk to developers like you to inspire them and help them build AI applications with or without MongoDB. And prior to that, I spent about 6 years working at the intersection of machine learning and cybersecurity. And outside of work, I love to read. I used to try to yoga pretty regularly till I busted my knee not too long ago. And I'm always on a mission to hit as many local coffee shops as I can. So in today's talk, I'll start off by talking about what AI agents are in the generative AI era, set the stage for why this conversation about memory is important. I'll then talk about the types of human memory and how and if they can map to agentic memory. And I'll spend a lot of time on how to manage, or as I like to call it, CRUD memories. And finally, I'll wrap up with what I'd like to be your key takeaways from my talk today. And I hope I've left some time for Q&A, but if I haven't, then please come find me after the talk at the happy hour or whatever. Cool, let's jump right in. Very quickly, let's talk a bit about what AI agents are. So AI agents have been around for a long time, at least since the 90s. These are some pictures I found from the 90s. So reinforcement learning agents were the original idea of AI agents, where a machine learning model selects from a set of predefined actions to maximize rewards based on some sort of environmental feedback. And this reward feedback loop is what helped these agents master games like backgammon, chess, Go, and even go on to beat the grandmasters of their time. But with the advent of LLMs, this definition has shifted a little bit, and now when someone says AI agents, they are typically referring to LLM-based AI agents. So in this talk, much like everyone else, when I say AI agents, I'm referring to LLM-based agents. But AI agents, whether they are reinforcement learning agents or LLM-based, have essentially the same main components. So there's perception, and this is what allows them to observe and interpret their environment. Action, which is how they interact with their environment. Then there's memory, and this is how they are supposed to maintain information about their past experiences, state, and knowledge. And feedback, which is signals from the environment or the user, and this is what helps guide their behavior. And then with LLM-based agents, there's an additional component called reasoning, which means they can now somewhat independently reason through a problem and determine the course of action to solve the problem. So in the context of LLM-based agents, perception comes from inputs to the agents, and these can be inputs from a human or triggered by a system like Slack or email. These agents take actions with the help of tools, which can be simple APIs like weather or search APIs, vector databases like MongoDB or some other database, and even specialized machine learning models. And the agent's memory comes from its past actions or interactions with the user or environment. And these are what also give agents feedback. So its feedback comes from tools it executes, and again, the user and the environment that it runs in. And finally, they use LLMs as the brain, and this is what helps them reason and make decisions. So then the definition of an AI agent during in the generative AI era becomes this. An AI agent is a system that uses an LLM to reason through a problem, create a plan to solve the problem, execute the plan using tools, and iterate on the plan using feedback from tools and its past interactions. And this is huge. With agents, we have augmented the world knowledge of LLMs, their reasoning and natural language understanding capabilities, with the ability to take actions. So with agents, a future of full autonomy, which is the eventual goal of artificial general intelligence, actually seems somewhat possible and freakishly closer than it has ever been before. But trust and reliability are a big part of us actually looking at agents as partners in doing things in the future. And the good news, and for some of us, I don't know, bad news, is that things are improving constantly and rapidly. Where we could interact with LLMs using only text just a few years ago, we can now interact with them using other modalities like images, voice, or a mixture of any of these. LLMs are also getting better at reasoning. Where we were used to going back and forth with these models to reach an outcome, we are at the point where we can give LLMs a goal and then have them plan, reason, reflect, refine, and do whatever it takes to arrive at a final answer instead of hand-holding them through the problem solving. But there's one aspect of agents that we don't quite hear too many people talking about yet, something that's truly important for them to augment our agency in the future, something that will allow us to feel comfortable putting them in charge of some of the steering of the metaphoric vehicle that is our own lives. And that's memory. To be fair, in most LLM applications today, we do see some form of memory, and it usually manifests in the form of chat history, which gives LLMs context of past interactions in a conversation to maintain coherent dialogue during the conversation. And this works in most cases for now, because the scope of what we use LLMs for right now is fairly constrained or limited. But as we expect these models to and agents to execute more sophisticated and complicated tasks, we are going to want them to be more intelligent than they are right now. Imagine if we only remembered our most recent conversations and nothing else. But we don't work that way, right? At a high level, humans have two types of memory, short-term and long-term. So let's talk a bit about these and then see how and if any of these translate into AI agents. So short-term memory helps us remember not just conversations from the recent past, but also other observations, such as the weather you looked up when you came up to SF this morning. Or there's even a shorter-term memory called working memory, which temporarily stores information that your brain is actively working on. So for example, if you're solving a math problem, any intermediate calculations you might make are stored in your working memory. But what really makes us the so-called intelligent beings that we are is being able to recall and learn from experiences that we've had over an extended period of time, also known as our long-term memory, which in turn can be categorized into a few different types, starting with what we call semantic memory, which is our long-term store of knowledge. For example, facts you learned in school, or a slang term you looked up that's painfully going to remain etched in your memory forever. Then we have episodic memory, which helps us remember and recall key events and episodes in our life, like that argument you had with your partner, I don't know, 7 years ago, or the day you graduated from college. That's me, graduating from college. We also have procedural memory that helps us learn and recall how to do things, for example, typing or riding a bike. And finally, sensory memory, which are memories from sensory stimuli. For example, a concert you attended that sounded really good, or a pizza or bread you baked during COVID that tasted and smelled delicious. But AI agents aren't human. They are software, or a combination of software and hardware. And if they're to truly have the kind of cognitive abilities that we do, we need to be able to translate the forms of memory that I was just talking about into software so that AI agents can use them. So let's see how and if the types of memory that I was just talking about map to agentic memory. So of course, there's short-term memory. Some of you have probably used this. And like I mentioned, this typically manifests as recent conversational history in LLM applications, which includes agents. But what we are focusing on today is long-term memory in agents. And let's start with semantic memory, which is the long-term knowledge of the agent. And agents intrinsically have some semantic memory because they have information encoded in the weights of the LLMs that they use as their brain. But we can also supplement their semantic memory via external databases or sources of knowledge. And these can contain any information that you think can help inform the behavior of the agents you're trying to build. For example, if you're building a customer service agent, this could contain documentation of the different applications that you want that service to support. Or if you're building a simulation video game, this could contain information about the different characters or entities in your simulated virtual world. Then there's episodic memory, which again is the memory of past events for humans. But in agentic applications, this translates to sequences of actions that the agent takes to complete tasks. So here's an example of what that could look like. Say it's a computer use case where an agent takes web actions to complete tasks. So you could have a generalized name for the task and a description, a natural language description of the series of steps taken by the agent to complete that task. Then there's procedural memory, which is essentially the agent's memory of how to do things. And again, agents intrinsically have some procedural memory encoded in the weights of the LLMs that they use as their brain. And then there's the agent's code itself that, for now, we define, which in turn defines the execution flow of the agent and constrains what it can and can't do. And while agents can't quite self-modify their weights and code, for now, at least they can modify their prompts. So say you have a system prompt for the agent, but during the course of its interactions with the user provides some additional information or useful instructions about how to do a thing. The agent can then update its system prompt to incorporate that information. And finally, there's working memory. And this is information that the LLM holds in its context window as it's working through the current task. And the working memory can consist of user inputs, outcomes from tool executions, the LLM's planning and reasoning traces, and it can also pull in memories from its long-term or external memory store into its current state. And we won't worry about sensory memory right now because this is a 30-minute talk. And I personally think AI agents are a little ways away from being able to process things like smells, tastes, and other sensory inputs. But if they're not, then feel free to correct me. OK, so at this point, we've spoken about what the different forms of memory look like in agentic applications. So now let's talk about what it takes to create and persist memories, retrieve them in a timely and efficient manner, update memories as new information is obtained, and delete or phase out memories to make room for new ones. So the way I like to think of memory management is it's a good old CRUD operation. So let's talk about creating memories. So like I mentioned before, agents aren't yet fully self-sufficient when it comes to creating memories. But thanks to LLMs, they have some forms of memory built into them. For example, the weights of the LLM are a form of semantic and procedural memory for agents. But we can also kickstart some of their memories. For example, we can create additional semantic memories for the agent by creating an external body of knowledge and giving the agent access to it via tools. We can also write detailed prompts or, again, create tools that the agent can use to create memories out of raw information. The way I see it, there are 4 ingredients that agents can use to create memories. The LLM's planning and reasoning traces, where it reasons through a problem, decides what tools to call, and makes observations after the fact. The outcomes of tool calls, including any logging traces within the functions or tools themselves. Conversations with the end user, if the agent interfaces with actual users, or feedback from the environment, if the agent is running in a sandboxed environment and it's actually modifying the environment itself. But reasoning traces and tool outcomes, the way I see it, are just the ingredients to create memories, but they're not memories on their own. Imagine if we were to store every single raw detail of every conversation we've ever had or every experience we've had. It's just not efficient or practical, and to an extent, it's just superfluous and unnecessary. So similarly with agents, you want them to extract specific insights from the information in its working memory and commit that to long-term memory. So for example, again, if you're designing a simulation video game, you might want the agent to extract like specific character traits or relationships between the characters in your game or notable events in the character's virtual life. If it's computer use agents, then you might want to log successful or even erroneous action sequences. Or if it's code generation, then you might want to log any human expert instructions obtained by the agent as it's interacting with a human, or even errors and what the resolution for that looked like. The other thing to think about when creating memories is when to create them. And I was trying this a couple of days ago, which was pretty fascinating. And I was doing it for a personal assistant use case. And I found that LLMs have pretty good intuition for when they should create, retrieve, and update memories. But you can also help them along in this process. So for example, you can prompt the agent to create memories whenever a new input is received, so it can inform every response. Or you can have it create memories based on a certain condition. For example, if the context window of the LLM is close to getting maxed out, then you do a memory creation operation. Or just something more deterministic, like after X number of turns in the conversation, have it call that tool to create memories. I thought that context window one was pretty fascinating and made a ton of sense because reasoning traces and conversations can get pretty long. So you run the risk of the context window of the LLM maxing out before the agent even has a chance to create memories. So I thought that was a pretty nice way to do it. Or you can also prompt the agent to create memories at the end of every conversation. And finally, you have the option to create them on a schedule, say hourly or nightly. But this choice depends on what the trade-off between adaptiveness and latency looks like for your application. Because at the end of the day, creating memories are an additional action that the LLM needs to perform, which means additional steps in the process, and that means additional latency. Another thing to think about when creating memories is also persisting them for use later, because without this, memories would reside in the LLM's context window and won't be available for future conversations with the user. So we persist them in an external database and retrieve them as and when needed into the working memory of the agent or LLM. And I do think this will change in the future, where I think LLMs might be able to fine-tune or flash-tune, as I like to call it, themselves with memories. But for now, I think we need an external persistence mechanism. So when persisting memories, it's also important to consider how to model them in such a way that you can retrieve and update them efficiently. And there are several ways to do this, as I'm sure you've seen with just building applications. There's so many different ways to store and model data. But I want to touch on some common important patterns. So all memories have a temporal aspect to them. So always good to have like a created or last updated timestamp. And what this does is it helps you do things like filtering by the timestamp, prioritizing for recency, phasing out memories, that kind of thing. And this works well for episodic memories. For memories about entities or procedural memories, such as system prompts, I think it's good to maintain a single source of truth that updates as new information is obtained. And the challenge you might run into here is you might need to periodically reconcile and compact memories to prevent unbounded growth, but there's some ways to deal with this, like summarization and stuff. Cool. So we've spoken about creating and persisting memories. Let's talk about retrieval. But before we talk about different techniques for retrieval, let's also quickly talk about when to retrieve long-term memories. This thing about when is pretty important because, yeah, like you could leave that up to agents, or you can introduce some control into the process. So with sims, you might want to retrieve memories before every action because, say, you want to inform what a particular character does next based on what it did previously, or you want to inform that interaction between two characters. Or if it's computer use, you might want to extract past action sequences during the initial planning stage of the LLM, so it you can help it with planning for the current task at hand. Or if it's code generation, you might decide that I'm only going to retrieve memories when I encounter an error to see if there's any resolution techniques in my past history. So when it comes to retrieving relevant memories, we can take lessons from building search and at this point maybe RAG applications and apply the same techniques to this new problem of memory retrieval. So the simplest search pattern that can help with memory retrieval is exact matching, where you retrieve information based on a definite set of criteria. So again, let's take the example of Sims. Say two characters are having a conversation. I can, if I'm able to extract the names of these characters, I can use this exact match pattern to extract the semantic memories that I have about both characters into the agent's working memory. Vector search applies here as well. And vector search, for those of you who aren't familiar with this technique, retrieves information based on intent and meaning using a special type of numerical vectors called embeddings. And this technique, if you've ever built RAG applications, is used extensively there, but also applies to this problem. So let's assume you've stored past action sequences of an agent in an external database. So then given a new task, you can use vector search to extract similar sequences during the agent's initial planning stage to inform this new task. Another technique that you may have come across is hybrid search, which combines the benefits of both keyword-based and vector-based approaches. So let's take the same example as before, where the current task that the agent is trying to work on is buying an item on Amazon. So hybrid search, in addition to getting action sequences for similar tasks, might also help retrieve or prioritize Amazon-specific sequences during the retrieval. And finally, you can also rescore and re-rank memories that are retrieved using one of these search techniques to include criteria like recency or importance. So let's take the example of a sim again. I somehow love that sim example. It's just so easy to relate with. So yeah, a sim where I have recorded episodic memories about this character called John Lynn. So say these two documents were the ones that were retrieved by vector search, and they have the scores 0.96 and 0.88. You can modify these scores by applying, say, a decay function on that created timestamp, which is why I said include some sort of timestamp. So notice how the older document is weighted slightly lower because I'm like, I want to prioritize more recent documents rather than older documents. And I can also add an importance score to include some sense of how important a particular memory is. And you can generate this score using an LLM during creation time. So let's assume I did that and I've stored that, persisted that to my external database. So for example, the memory of John going to sleep every day is less important than the memory of John getting married. So I weight the importance of the memory of him getting married higher. So this way you can create a more holistic scoring and retrieval mechanism for the agent's memories as well. Okay, let's briefly touch on updating memories. So as agents learn new information over time, some memories might need to be corrected or updated. And the easiest way to do this is to club the retrieval, creation, and update operations together. So at whatever cadence you decide for memory creation, you would also retrieve relevant memories, update them with new ones if needed, and store them back to your external storage. And here's an example of what that process might look like. So say you persist your agent system prompts to external storage. When the agent is first invoked, you retrieve the prompt and say it's a prompt for code generation. Then during the agent's interactions with the user, say the user mentions like, hey, each time you generate a function, also include doc strings for that function. So then the agent can use this new information to first create a memory out of it, reconcile it with the memories it retrieved, and write this updated memory back to the database. And finally, let's talk about deleting memories. Why would we want to delete memories? Wouldn't it be awesome if agents could remember everything they've ever done or learned? Not quite. Basic storage is cheap, but if you want enterprise-grade storage and retrieval with things like redundancy, backup, and fast access, then these costs are going to increase exponentially as your data scales. It's also wasteful to continue to store data, or in this case, memories that haven't been used for a long time. And finally, more isn't better if you can find memories and can find things that you need and find them quickly. So phasing out unused memories can help improve the retrieval performance by keeping the search space and the latency of your applications manageable. So we want to delete some memories from time to time. And the way to go about this is the way you handle any other data, which is by typically imposing some sort of data lifecycle policy. So you would monitor, the way I've done it in the past is monitor usage patterns and move unused data to cheaper, slightly slower archival storage at a certain cadence that you determine based on looking at those usage patterns. And regardless of usage, you'd also impose retention periods to periodically delete the oldest unused memories. And that's it. That's my speed run of how to think about managing long-term memories in agents. And I know I'm almost coming up on time, so I wanted to quickly wrap up with what I hope will be your key takeaways from this talk. So first one, memory manifests differently in different applications. You might have the same types in every application, but the definition of what they mean will differ. So as we saw, like things look very different from like a SIM to computer use to something else. Not all memories are equal in terms of how they are stored, when they are retrieved, and how they are updated. So if you're thinking about memory management, then you might have to think of different management mechanisms for different types of memories. Storing all memories from the beginning of time is not practical at scale and honestly wasteful. And finally, I think long-term memory management is a key component for AGI. So right now, it's through external memory systems, but in the future, I think this might be embedded into the weights of LLMs themselves. But no matter what the mechanism is, I do think for AI agents to achieve their full potential, we need to be thinking about memory management. So I really hope that as you build more complex agentic systems at work, you will think about long-term memory. And here's my LinkedIn QR code. If you'd like to stay in touch, I hope you will. And I think, oops, let me go back. That's it from me. I think we have time, like a minute or so for questions. Yeah.
So, I'm curious about your comment about the difference between logs and memory. Because I noticed that you actually have experience in that search kind of things. Previously, we can log everything, but we can have the flexibility when for later, right? We can.
Sorry, there's a little bit of noise. Could you repeat that, please?
Oh, I just wonder how's your take about the difference between logs and memory?
Logs and memory.
Because previously we log everything.
Right.
But we can have flexibility when we try to analyze any strange things, the use case can be postponed later. And when we do the memory, like you introduced, we let the LLM to make a decision what to store.
Yeah.
Sometimes we already made some decision when we store. So because you are also the log expert, I noticed your experience have in Elasticsearch. So wondering what's your take about the logs and memory?
Yeah, so I think it's the use case is slightly different, right? Like if you want to search over all your data, if you're building a RAG application, then they're storing like all your data just makes sense. But if you want to store data as memories for the agent, then you don't need that level of detail. So I think it just comes down to like two different use cases. So yeah. Right. I think I can unplug this. Yeah.
Can the long-term memory benefit help avoid hallucination or reduce hallucination?
It could. So, for example, if you're logging episodic memories and you have like a computer use case or code generation where you're logging errors. So again, depending on what you're logging to memory, it could help with reducing hallucinations or making the agent more reliable, right?
Or if you don't update your long-term memory, then it can create hallucination as well. So.
Yeah. So like if it doesn't reconcile memories in an accurate manner, then it might just like make up stuff. So like this morning, I looked up some information about a MongoDB sticker, and then I asked it like, hey, what do you know about me? And he's like, I think you really like MongoDB stickers, and you're like a mysterious techie or something like that. So if that's how it interprets what I'm asking it, then yeah, it could also lead to more hallucination.
Thank you.